Let's look at a numerical example, and it'll help to draw out some of these subtleties with the F distribution in doing hypothesis tests associated with ratios of variance. Right, now we'll go back to the aquifer data of example HT 3.2, that's the Ogden Valley aquifer data, and as we answer the basic question, are the variances between the discharge and recharge significantly different? And you might even suggest that, well, gee, based upon an engineering analysis of just the significant digits associated with these numbers, you'd be tempted to think there's not much difference here, and that'll actually be borne out from a statistical hypothesis standpoint, significance standpoint. But nonetheless, let's illustrate the procedure here with what we see from a common sense approach. It sure doesn't look like these are much different. Okay, so the parameter of interest are the variances of the discharge and recharge. Okay, and the null hypothesis is going to be that sigma 1 is equal to sigma 2, or the variances are the same. Right? The alternative hypothesis is that they're not, so this will be a two-sided test. And we'll look at this ultimately at the alpha 0.05 level. Our test statistic that we're going to use will be F, defined as the ratio between those two sample variances, and under the null hypotheses, since those are the same, then they cancel out under the null hypothesis, and we're just left with this as our test statistic. Right, and numerically, let's go ahead and perform the computation now. Then that equals 2197 squared divided by 2223 squared. And these numbers do get quite large, so depending on how you want to process that, I like to actually divide first before I take the square. Obviously it doesn't matter, do it any way you like. And we'll get 0.9767, or about 977 for that particular number. Right, now, the operating rule that we're going to follow here is that we'll reject our null hypothesis if, right, well, our situation is that n1 is equal to n2 is equal to 17, and we're going to let our significance level be 0.05. And so if our statistic is larger than our upper tail, so 0.025, in this case 16, 16, they're the same, so we can be a little bit sloppy about which one is which, but we really don't want to be, right? That's U and that's V. If that is larger, or if, on the other hand, at the lower end, this would be 1 minus that alpha, two-tailed, right? That's why that's 0.025. So that'd be 0.9725, 16, 16, which is equal to 1 over F 0.9725. 16, 16, where you swap the roles of those two, sorry. And this is why this is so easy to get this screwed up. This is a 1 minus alpha deal here. It's 0.025. Or did I make that mistake just to illustrate how you could make a mistake? No, I'm not telling you. Right, so that easy to make mistakes here. You got to flip-flop the roles. In our case, again, the 16 and 16. There's an example in the book where they do keep track of that very carefully, and that's important, of course. Now we got to go back to our tables, our F tables, to get this, or computer program, if you like, doesn't matter. Here are a couple of things you got to keep track of. One, that we have a different entire table for different tail areas. Right, with 2 degrees of freedom, the tables get real large real fast, and we really have a three-dimensional surface that we're trying to deal with, in volumes really that we're working with under that surface. But we've taken little individual slices of it to get here to a single table value. Alpha equal 0.025. That's the one we want, right? And there's your degrees of freedom. And again, you got to keep track of what order is what. So nu 1, nu 2, yeah, right, different symbols now that they use here. And degrees of freedom for the numerator is nu 1. Right, so that goes along the top. That's each of the columns. And then along the rows, we get degrees of freedom associated with the denominator. Again, for our illustration here, they're the same. So 16 going on out. And note that we have an irregular scale. Right, it goes 1 through 10 in increments of 1, then 10 to 12, and then 12 to 15, and then 15 to 20. Kind of a pain, I know. So as we go on out, 10 to 12, and then 12 to 15, then 15 to 20, we're at degrees of freedom minus 1, so we're at 16 on each. Right, so 2.79 to 2.68. I don't really like to linear interpolate. This is highly nonlinear, but it is somewhat smooth, and so we can kind of guess just by a little bit of linear interpolation. It's probably going to be close enough. So 2.78-ish would be about the right value for that particular one. So we have then that this number is going to be 2.78. And this number down here, because the 16s played out to be the same, is going to turn out to be also it's the same number, 2.78. And in this case, 1 over 2.78. Alright, and that number is 0.3597, or about 0.36. So 2.78 reciprocal of is about 0.36 or so. So clearly then we have an F statistic of 0.97. 0.98 is between 2.78 and 0.36. So we fail to have strong evidence to reject the null hypothesis. Certainly makes sense. After all, as I said before, engineering common sense says that, gee, these two numbers here and here sure look about the same, and even to 2 digits they would certainly look the same, and so why should we expect there to be any statistically significant different number there? Okay, now let's go back to the tables and illustrate one of these crucial concepts here, and that is how important it is to keep track of the numerator denominator. We'll take 3 and 8. Right, so here's an 8 and there's a 3, right, 5.42. If this were symmetric, we ought to be able to go 8 and 3, 3 and 8 should be the same thing, right? So 5.42, and we come out 3 and 8 on the other way, and we get 14.54. They're clearly strongly different numbers, and so you do have to be very careful in how you work this out. In our case, it was easy because the two numbers are the same, so we could be kind of sloppy about it, but in general, you can't do that. One more thing to take a look at, and that is the type 2 errors that we get. And here in the type 2 errors, remember that's the likelihood that we fail to reject the null hypothesis when we really should. I'm sorry. Yes, that's right. It's confusing. Fail to reject the null hypothesis. In other words, we really want to get to the point of accepting the alternative hypothesis. And so these, and remember the chart 7s are the operating characteristic curves under special cases. This special case is that the sample sizes are the same. Right now they don't say that in these tables themselves. Right? That kind of bothers me a lot that they don't. They just assume you know and that you've read the book, and back in the book it tells you that. Right? So that's kind of crummy, but it is what it is. And so we've got operating characteristic curves for different values of n for the two-sided f-test for a level of significance of 0.05. Okay, so wow, right? So two-sided f-test for a level of significance of 0.05. The one below is 1% significance. Right, now note that when lambda is equal to 1, well, what's lambda? Lambda is the ratio of sigma 1 to sigma 2. Right? So that's something else they really should have in here. Right? But note what that value is when that is equal to 1. And it's, 0.9.95. So that's the beta value. Ooh, that's real high, but 0.95, that corresponds directly with this 5% significance, right? And so what we're hoping to do is we're trying to demonstrate here with the operating characteristic curve the beta probability that we fail to reject our alternative hypothesis, that we have falsely accepted the null hypothesis that says the two are the same, right? And so, wow, those all converge to the same point, right? These are different curves for different sizes of n's. Notice how fast these curves drop off, though, as this ratio gets a little bit bigger. So if we set up our test, if we have the expectation that these variances are different, well then, and by the way, it dawned on me that I'd have to go look in the body of the text. Is that supposed to be sigma 1 over sigma 2, or is it the variance of 1 over the variance of 2? I think it's this one, but you'd have to double check. Again, it really should be right here in the table, but it's not. And so note how fast you fall off if your sample size is large. Right now, obviously, if the sample size isn't as large, it doesn't fall off quite as fast. Right? And this is the probability of accepting HO. This is this beta probability, actually, that we're reading off up here. So very careful that you be very careful when you're reading these guys. This is chart O and P for two-sided f-tests. And then over here you have operating characteristic curves for different values of n for the one-sided f-test. All right, wait a minute. Different values of n. Well, they mean different n values, but they don't mean that n1 is not equal to n2. Oh, see, they do have it there. It's just in that tiny little print. And that would be real easy to drop off and not see. Someone out there is saying, oh, I saw that before. Where were you, Dr. Schmucker? Come on, get with it. Yeah, was I just testing you? Could be. I'm not telling. Right, so note that they do have it, but boy, it's really tiny and it's easy to miss that, right? And so note, this is for the one-sided f-test, right? Again, two different percentage values that are at work there, right? And then finally, there's confidence intervals for the ratio of variances, and those are fairly straightforward, and you can take a look at those in your book. Nothing too particularly tricky as you work through there, other than, once again, you just have to be very careful to keep track of the nomenclature and the subscripts that go along with those.